Hey everybody, I'm Will from PC World, and I'm here with one of our favorite contributors, Dr. Ian Cutress, aka Tech Potato. Welcome back.
Yeah.
Hello, sir.
Great for inviting me. How's it going?
It's great. I always love bringing you on here and asking the kind of questions that stump Adam. So I'm gonna get right to it and just ask, hey, what's going on with foundries?
Yeah. Turns out making chips is really expensive.
Like really expensive, billions of dollars expensive. Big B. Yeah.
It's not only that, it's when they're not when you have one, if you're not processing it at like 95% plus capacity, you're losing money per second. We're talking thousands of dollars per second.
Do they have like one of those signs on the wall that's like, it's
this is
15 seconds since we last made money?
Yeah, that sort of thing.
Why? So one thing I learned recently is that there's kind of a separation in types of foundries. There's like advanced foundries, and then there's everybody else. Can you kind of explain that? Because I think we're talking about advanced foundries here, right?
Yeah, it's if you're going from completely brand new, de novo, greenfield sort of design, you first have to obviously buy the land, get the permits, deal with local government, maybe negotiate some tax breaks because you're providing a service to the economy, make sure you have the contractors in place, and then stage one is build a shell. So this is literally just build the building where you're going to have your fab inside. And these takes different sizes. You'll have anything, and usually fabs are measured in wafer starts per month. So that's how many wafers start on their process each month in the fab. And it's usually a metric for clean room space.
And the wafer in this case is big disc of silicon that they run through a bunch of machines, and at the end you get chips that get in your phones and watches and computers and everything else.
Yes, I'm sure we've got a picture of me trying to bite a wafer that we can put on. But yeah, it's also slightly dependent on the level of technology, the process node of the technology that we're going after. And in normal parlance, a gigafab, which is what TSMC talks about, is 100,000 wafer starts per month.
Okay.
And they have at least a half dozen, if not a dozen of those.
And they operate around the clock, I assume.
Yeah, these are 24-hour processes. I think Intel's fabs in Israel have 1 day off a year.
Okay.
But they are monitored. Everything's being processed. Everything keeps going. So once you have the shell, that's kind of that's your start of climbing the mountain. A modern fab shell, land permits, build out is about $2 billion.
Wow.
Just to get there. That's to get to the stage of, I guess, anywhere from, say, 50 to 100,000 wafer starts per month.
And that's before you put, like, clean rooms and a bunch of machines and stuff inside?
Well, so that's the second stage. The first stage can take anywhere from 6 months if fast-paced, up to 2 years if it's almost all done by the book.
And this is the thing that we have a pretty good understanding of how long this takes in different countries. Like the average is I think 600 days from start to first wafers coming off.
I've heard of times sub. If you're going for the full build, you could probably do it in under 2 years, maybe 15 months if you push it really hard. But that means construction round the clock.
Yeah.
The problem comes that once you have the shell and you start to put the tools in, so a modern chip on the wafer has to go through a series of machines where you're spinning a coating, then you're using your lithography, and then you're doing etching and doping. A modern chip making process goes through over 1,000 of those steps. And so you've got
each one's a different machine, presumably, or a pass back through the same machine again.
Yeah, so some of those steps will be identical depending on what you're doing. So a modern processor, for example, has 17 metal layers. And each one of those layers has multiple steps involved, and some of them may look similar, and the ones right at the bottom need all the advanced lithography, and the ones higher up don't need as advanced lithography to do it. But as a result, you've got all these wafers going around the fab, and the whole point is to maximize your machine utilization.
Oh, I know. I played Satisfactory. I know how this works.
Yeah.
You have to go out and get the slugs, and then you put the slugs in to overclock the slow machines so that the fast machines get fed on time.
I don't think any machines in the fab are overclocked. I'll have to ask next time
Okay.
I'm there.
Okay.
But yeah, also it depends what you're making, so you can have the right configuration. So right now there's talk of things like digital twins from NVIDIA where you can map out your fab before you buy the tools.
Wait, they need to make a game for this. I would play this game.
Fabtory.
Please.
Fabtory.
Wait, cut this from the video. Don't put this in the video. Okay.
But you have to go to the tool companies themselves. So these are companies like Applied Materials, KLA, Tokyo Electron, even Nikon and Canon. You have to say, oh, I want to go buy the tools.
And the tools are phenomenally expensive, I assume.
Tools are expensive, but in the case of, say, EUV machines from ASML, there's a backlog. You buy one now, you won't get it for at least another 12 months. So should you buy now and hopefully you'll be ready, or do you do you put an order in for 3 and hope you'll get 1 on time?
And like the penalty if you get it too early is it sits idle and isn't making money when you're paying for it. And if you get too late, then your entire factory is not making money.
Well, for the biggest machines, ASML will send a crew out to install it for you. And installing an EUV machine can take up to 6 months.
Oh, wow.
Because you've also got to build it. These things are 100,000 components, megawatt lasers, and droplets of tin. And I've seen one half built in a fab, and it's just a marvel of engineering how it's done. But then you've also got the power underneath in what's called the subfab. And then once you build it, you've got to tune it and dial it in. You've got to essentially do equivalent of fettling to get it dialed in so you have the right configuration to actually go and build the chip. And then once that's ready, you can start to do your first test chips to make sure everything's going through.
And when they're doing the say you're Intel, you're working on the 18A process node right now, which is what conveniently they are.
Mm-hmm.
You have the first chips coming off the line. Are they can't just take like an old design. They can't take like a Skylake.
No.
They have to take something that actually is built for this new process.
So most foundries will run, even when they're developing a node, what's called test wafers. So rather than having CPU cores and memory and stuff, it will be parts of that. So how do we do power control? How do we do memory or SRAM or caches? And you'll see, if you go to AliExpress, for example, and try and buy a wafer, you can get them for about $60, a small 8-inch wafer. That's just excess from a foundry that they have out there. It's likely to be a test chip pattern. And the idea is you're testing for regularity, you're testing for defects, you're testing for yield. And as you ramp up, you may be starting to test for frequency on top of that. And so you have this... The way chips are manufactured is almost considered 100 degrees of freedom, task. And if you try and make one part of that process better, 3 others might get worse.
Oh, so you're pushing wallpaper bubbles down constantly.
Yeah, you've got to dial it in, and that's part of the process of building up a fab. Now, you could argue, well, can you not start doing that while some of the tools are being installed? You can, but then you're disturbing your clean room environment. Because don't forget, these things are made in clean rooms. I think it's 1 to 10 particles per square meter, per cubic meter. And you have an airflow from top to bottom that's laminar. So and they have cleaners everywhere, always cleaning, always trying to get rid of all this dust.
Just because we're naturally filthy, horrible animals.
Yeah. I was once at Global Foundries fab in Malta, so upstate New York, and they said at any one point, we have this massive fab that does tens of thousands of wafer starts per month, and at any one time we have at max 12 people on the floor because it's all automated.
Yeah.
Now that's a modern fab. You may not consider it leading edge because it's not 5 nanometer or 3 nanometer, but there are still so many fabs now that are 90 nanometer and 120 nanometer, and they can be fully manual processes as well.
So it takes a long. Okay, so at this point we're looking at 2 years plus before we start seeing anything come off the line, and then from that starting to ramp, and then the dialing in. How long is the dialing in going to take? We're looking at months, days, weeks, years.
So on the most leading edge processes, we could be looking at a year.
Oh, wow.
So you dial in the machine individually, and then you dial in the process to make sure it works. If it's a known process that you're licensing from someone, so say you're building a 28 nanometer fab from this technology provider, it's already been proven in other fabs. So in order to dial it in for yours would be a simple process.
It's the same as Satisfactory. You copy your settings from one area to another one, and you're ready to go.
It's a process Intel calls copy exact.
Okay.
So you try and copy exactly what's in a previous foundry in this one.
Is that like all the way down to like floor layout and things like that?
Almost, pretty much, yeah. Given all the potential differences there could be for a given environment.
Yeah.
But if you're going through a new process, you've got to find out what's the best way to deploy it. So if we look at the latest generation, research and manufacturing nodes, before they get pushed into a new fab, they're optimized in one that's in a small area of a fab that already exists, such that when they get it right, they can then copy and replicate
Scale it up to handle the parallelism of the process.
There is a slight difference whether you're building a fab for your own products versus whether you're building a fab to make somebody else's, because you may have a partner who is heavily invested in having your process up online because it helps with their costs. And they may be willing to accept slightly lower yield if they can be the priority customer in what you're building. But yeah, it's commonly the stages of building a fab are permits and shell, then tools, and then ramp.
Okay.
Test and ramp. So you have 2 billion, and if we're going for a leading edge, mega fab.
For 2 billion for the shell.
To the shell, then anything up to another 18 to 25 billion for the tools, installation, and then ramp and test as well.
And ramp and test is another. Might just throwing a couple billion in there just to cover it.
Yeah.
I think Intel, when they canceled 20A, said it was going to cost $500 million to get it from where it was to online, right?
That's because what they were planning to use for 20A is almost completely recyclable for 18.
Ah, okay.
Right. So they were able to do some translation and transference. It's the same with 4 and 3.
Okay.
So they announced that Intel 4 was in their Ireland fab. I was there earlier this year at the official announcement. But that fab is to do 4 and 3 because the processes are so very similar.
Got it.
The equipment crossover. And that's always a common thing when you're either updating a fab that already exists or installing into a new fab. How much equipment that I might have in another facility can be reused for this?
So then, so we're talking $20 to $30 billion to get this online, it sounds like.
For a leading edge.
For leading edge, advanced.
High volume.
Yeah. Like bespoke, but not exactly bespoke process.
I think Intel quoted 10 billion to 20 billion a fab for the new ones they're building.
So then what's the life cycle like on this fab once they build it? Like, are they going to be making these advanced lithography parts in this shell for 20 years to work out the cost on this?
So there was a statistic a while back I read that 90% of all fab equipment that's ever been built is still in use.
Okay, that makes sense.
So some of it does get resold. Funnily enough, I was at a conference, and your badge gets scanned by companies randomly. A company scanned my badge, and I get emails from them about once a month about the new fab equipment they're selling that's all secondhand. I think they're listed as like a Global Foundries equipment reseller. So any of the lower end fabs who want to pick up that equipment that may be anywhere from 5 to 10 years old on the cheap, can have those facilities to do it.
50 grand probably, right?
Yeah. The only time you get that secondhand equipment on the market is when either a fab's being updated or a fab's being mothballed.
I was going to say, because often, like I know that we're constantly updating fabs and like turning, say, something that made EEPROMs for the last 30 years into something that makes something else now. Like, I assume it's a similar process. So you already have the shell, which means you already have the floor, but then you have to look at like what the like we didn't even talk about the supply chain that these things need to work, because you need to have all sorts of exotic materials coming into these places all the time too. It's I guess every time I've looked at this, every time we talk about this, I just realize it's like 4 or 5 layers more complicated than I imagined it could possibly be before.
Well, you got to make sure if you're upgrading a fab, whether it has enough water and cooling, whether it has enough power. So if you're going from regular manufacturing lithography tools to EUV or the new high-NA EUV, that's a 10x increase in the power consumption of one component in your fab. do you have enough thick high amperage cables to supply power for those lasers, and then again vaporize the tin and make sure it all works. So it's almost the way we look at data centers today.
Yeah.
Right? Some data centers are limited in capacity and power, so you can maximize what you put in. But if you want to get the latest and greatest, for the new AI factories, you have to go build bespoke and new, and maybe have a facility to deliver that power independently.
So the last thing I want to talk to you about before, because we're almost out of time here, but what is the water used for? Like, water is always one of those things they list as we have to have a lot of water for foundry.
Yeah, it's a lot of cooling.
Okay.
It's a lot of cooling. There are some processes in in manufacturing that are, there's wet lithography, though I suspect most of those liquids aren't water-based. Water can be very aggressive given that it's a polar solvent and everything else. But typically, one of the criticisms when building a fab is, well, this place doesn't have enough water. One of the things that new fab developments do, and especially here in the US, agreements have to be made that X amount of water has to be recycled. If you're using it for cooling, it's not lost, but you still got to treat it before you put it back into the into the system. But also, fabs will sponsor water reclamation projects in the area. Mm-hmm. So people talk about Arizona not having enough water, Phoenix not having enough water. So it actually makes sense for companies that build in that area to turn around and say, actually, we're water neutral to the environment, or even water positive to the environment. And that is something that maybe fab companies from outside the US wanting to build new in the US, they haven't maybe not have had to deal with that before in their countries of origin. So that's again another point where the complication lies. Not only between the work ethic, but also the regulatory differential.
Fabulous, Dr. Giancountras, thank you so much. You can find him at Tech Potato on YouTube, and you can find us on this channel right below. Click the button to subscribe. We'll see you soon. Thank you.
Thanks.